Okay, in the previous mini lecture, we used these data to introduce you to the Pearson correlation coefficient. And if you'll recall, the Pearson correlation coefficient is an inferential statistics procedure that allows us to test for association. Now, what I'm going to do in this mini lecture is I'm going to use the same data. Again, our data here, column X has to do with the number of sales calls that a person makes, and column Y has to do with the total dollars of sales that the salesperson generates. So we're going to work with the same variables here, but rather than merely doing a test of association, we're going to perform a simple regression analysis, which is our first venture into what we call predictive modeling. If you look at Chapter 12 in Orris's textbook, and if you look at the first mini lecture that I did on beginning to introduce you to Chapter 12, you'll see that this formula right here, y equals a plus b times x, is the basic formula that we will work with when we do simple regression analysis. Let me remind you that y is our dependent variable. That's what we will eventually be trying to predict. A is our y-intercept. In other words, what do we predict to be the value of A when our independent variable x is equal to 0? And then our b times x product here, x is our independent variable. In other words, we're going to observe x to predict y, and then b will be referred to in Chapter 12 in two different ways. It will sometimes be referred to as the slope of the regression line. Alternatively, it will be referred to as b will be the amount of change in b will be the amount of change in y that we predict for every 1 unit change in the value of x. Okay? So again, this mini lecture simply builds on the previous one on Pearson correlation, but now we work with our data to do predictive modeling using simple regression. Now, running this in Megastat is no big deal, but to save some time, I've already conducted the Megastat process to perform our simple regression model, and this is what we get for our output. Let me remind you here that the model for a simple regression is y equals a plus b times x. Now, this whole set of output here is typical of what you would get from Megastat or most any other stats program when you conduct simple regression. But I want to direct your eye to several things that are especially key in terms of working with simple regression output. First, you see here that I write the hypotheses as b equals 0 for the null hypothesis, and b does not equal 0 for the alternative hypothesis. Now, if you go, well, wait a minute, what's b? Let me remind you the basic regression model here. Y equals b times x, and b is either the slope of the regression line, or we would say that b is the amount of change in y that we would predict for every 1 unit change in x. So when you look at our null and alternative hypothesis, we're basically testing the null hypothesis of is b equal to 0. It may not be obvious to you right now, but if b is equal to 0, then our independent variable x does not help us predict our dependent variable y. And that gets at the very heart of simple regression. Does our dependent variable x help us predict does our independent variable x help us predict our dependent variable y? The next thing that I highlighted and made it in a little bit larger font is R. And remember, R denotes the correlation coefficient of the observed sample. Notice here that our observed R is 0.893. I'm going to scroll up to the correlation matrix that we looked at in our previous mini lecture, And notice here that we showed the correlation between variable x and variable y was 0.893. And not surprisingly, we get exactly the same correlation. After all, we're working with the same data. So we get the correlation coefficient between variables x and y in our simple regression output. And again, this value ranges in an absolute value sense from 0 to 1. The larger the number, the larger the value of r, the stronger the linear relationship between two variables. So with a correlation of 0.893, we would conclude these variables are very strongly positively correlated with one another. Now, I highlight this, even though I won't spend much time on it here. R squared is equal to 0.798. R squared is what we refer to as variance explained. Okay? What we mean by that is the amount of variance in our dependent variable y, how much of that is explained by our independent variable x. And in this instance here, you can see that our explained variance is about 80%. That's very good. You might also take a calculator or Excel and check it out. If you square 0.893, you will get the value 0.798. Okay? So now let's go down, keeping in mind that the simple regression model is, as we have it here, y equals a plus b times x. Let's go down and actually look at the regression output. And the bulk of the regression output resides right here. Okay? I'm first going to direct your eye to this p-value, which is 1.14 e to the minus 7. That basically means that is a really, really, really small p-value. It's like 0.000000114. So that's a lot less than 0.05, our critical p-value. Okay? So by looking at this p-value right here, we reject the null hypothesis. And remember, our null hypothesis is that b equals 0. In other words, our null hypothesis is that our independent variable does not help predict the dependent variable. Well, since we've rejected the null hypothesis here, we conclude that b is not equal to 0, and therefore our independent variable x does help us predict our dependent variable y. Now what I want to do is move you to the next question. Okay, given that we know that our independent variable x helps predict the dependent variable y, how good of a job does that do? When I say that, the independent variable, how good of a job does the independent variable do in predicting our dependent variable y? I'll direct your eye back up here and say, to answer that question, we look at these r and r squared values here. When you have an r value that's as close to 1 as we have here, r equals 0.893, not only do we conclude that the two variables are strongly correlated with one another, we also conclude that our x variable, our predictor variable, our independent variable, does a really, really good job of predicting y, our dependent variable or our predicted variable. Okay? So based on our inspection of r at 0.893, we conclude that not only did we reject the null hypothesis and conclude that the independent variable x does a good job of predicting the dependent variable y, not only did we reject the null hypothesis, we also, based on our inspection of r, we also concluded that the regression model does a really, really good job of predicting our dependent variable y. It does such a good job that our independent variable x explains about 80% of the variance in our dependent variable y. I'll repeat that. Our independent variable x explains about 80% of the variance in our dependent variable y. Now, remember, I'm going to move your eye down here to this portion of the screen now. Our simple regression model, as we've talked, is y equals a plus b times x. I now begin to use the output from Megastat to fill in what's A, what's B. So here our dependent variable is our dependent variable Y is dollars of sales that a salesperson would generate. And you see this number 2.406, that basically means that we expect the salesperson to generate about $2,000 of sales for every sales call that he makes. Minus 1.008 is our y-intercept. In other words, what do we predict for sales when the salesperson doesn't make any sales calls? And we would predict minus $1,000 in sales. Okay? Now you might say, it's impossible to generate negative $1,000 in sales. Well, it is, okay? But we're working with predictive modeling here, and just based on the data that are available to us, this model just happens to yield a y-intercept of negative $1,000. Nevertheless, I want you to see how we make this transition from y equals a plus b times x down to our regression model, sales equals minus 1.008 plus 2.046 times the number of sales calls. Okay? Up here, you see that our predictor for B is 2.046, and thus 2.046 down here in our regression model. You see here that our predictor for our y-intercept, A equals minus 1.008, and that's why we insert the value minus 1.008 here in our regression model. Okay? So we make the transition. We make the transition from correlation analysis. The two variables are correlated at 0.893. That's a strong positive correlation between our two variables. We make that transition from the correlation analysis down to simple regression. And our simple regression model is y equals a plus b times x. Our simple regression output also provides us the Pearson correlation coefficient. We write our null and alternative hypothesis in a way that we predict in our null hypothesis that our regression model does not help predict our dependent variable. We read the p-value, which leads us whether to reject the null hypothesis or fail to reject the null hypothesis, and then to come up with what we call our parameter estimates. Our parameter estimates for A and our parameter estimates for B, we extract those from this portion of the regression output. And our prediction for A is minus 1.008. Our prediction for B is 2.046. So hopefully, without confusing you too much, that gives you your initial foray into simple regression. Thanks.